today's topic is called the Lagrange multiplier, okay? And that's something totally new. So if you haven't been doing homework, now is the time to wake up and catch up over this long weekend. So let's find the absolute max and min of this function, okay? And of course, that thing looks like this, paraboloid. And at the moment, it does not have any maximum, right? It only has a minimum, which is this. This is absolutely absolute minimum, but we have some constraint within this region, circular region, okay? So I'm going to cut this thing. So I think of it as some kind of cookie cutter. So I'm going to put x squared plus y squared is equal to 1. Okay, so it creates this kind of looking thingy. You know what I'm saying? So only the paraboloid that exists is inside of this thing. So in that case, this becomes our maximum, doesn't it? And then there's only another one on that side right there. Good. Looks good. So looks like our maximum is along the, this is x-axis. So when 1, 0 is the location of maximum, and also negative 1, 0 here, right? And that will be the local minimum, right? I have a better picture, which is in the Dropbox notes, so I'm going to copy that over. Looks like this. We enlarge it. So this is the part that I cut. So this top part does not exist. So just there. So this is the maximum, absolute max, and one on the other side, and this is the local. And this is the absolute min. So only that portion, the lower case, after cutting this thing out, exists. You understand the problem now. Okay? So, shall we take a partial derivative for the interior? Okay, I'm gonna see it like always. I want you to sketch this thing, the region. So let's sketch it right here. This is the region, which is let's move that a little bit so that it lines up like that, right? 1, negative 1, 1, negative 1. So far, so good? Okay. Now, so in interior, we'll take a derivative with respect to x. And that gives us 4x. Good. And then we'll take derivative with respect to y. And that gives us 2y. So far, so good? And we have to set both of them to 0. And that just tells you that x is equal to 0 and y is equal to 0, right? So that gives us this coordinate 0, 0, which kind of confirms our idea. That's going to be our minimum. Okay, this is the interior part. And on the boundary then, how are we going to calculate this on the boundary? Now this is circular, so it's like, you know what I'm saying? If it's rectangular, then we actually hold one of the variable as constant and plug it in. But if it's circular, we are forced to do this. So this is a boundary. How about this? We parameterize it. You know what I'm saying? That gives us this circular boundary. So instead of x and y, I am changing all of this as a function, single variable function of t. So our f of x, which is a function of t now, and y, which is a function of t, will become 2x squared. So we have 2 cosine squared t plus, and now y squared, so sine squared t. How about that? Good? Say yes. Should we convert one of this to the other one? So this, let's say this is 1 minus cosine squared. right? And one of them cancels, so this becomes cosine squared t plus 1. Are you with me? That is the equation of this. It's a cosine function, cosine square function, the yellow curve wrapped around the cylinder. You with me? Okay, then I'm going to take a derivative now with respect to t. So that will give me negative, eventually 2 cosine t and chain cosine ta. And before we set it equal to 0, using the identity, this is of course sine 2ta. You guys look lost. You with me so far? Now we set this thingy equal to 0. Right, then t is equal to 0. T is equal to pi over 2. That still gives you 0 here. And t is equal to pi. Or I'm not going to write over. And t is equal to 3 pi over 2. So far so good? You with me? And what are the coordinate x and y? When t is equal to 0, according to these two, this thing gives you 1, 0. This thing gives you 0, 1. And this thing gives you negative 1, 0. And this thing gives you 0, negative 1, doesn't it? Are you with me so far? And that thingy, we are on the boundary, so let's go back here. See, 1, 0 is that one right here. 0, 1, if this is y-axis, is that one right here. And then here's a negative 1, 0, and this one is 0, negative 1. So far, so good? So we are calculating, well, we have got these 4 values here, 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 here. Good. Any question before I move on? So we evaluate this function at all of our candidates. So we have f of 0, 0, which will of course give us 0, and f of 1, 0, and that gives us from here 2, right? And f of negative 1, I'm gonna do it sideways. F of 0, 1, and that gives us 1 from up here, right? Because y is equal to 1, x is equal to 0, and negative 1, 0 gives us 2, and f of 0, negative 1 gives us 1. So we can say this one is absolute minimum, and these two are max, which is exactly what we expected from the picture. Do you have any questions before I introduce Lagrange multiplier? Okay, technique of Lagrange multiplier. This is actually not too bad, but some of these problems can be pretty complex, so it is just converting calculus into algebra. I'm not sure if that is blessing or curse, because considering all of our algebra skills or lack thereof, that may not be such a nice thing. But let's just take a look at it. I'm gonna change this thing into contour math, okay? So graph instead of surface. Wait. Okay, I have to get rid of the second one, so I'm gonna have to manually throw that one in. Okay, now. So this is a contour map of our thing. Good. Okay. Now I'm gonna take a picture. Actually, I'm gonna zoom in. It doesn't want to zoom in. It doesn't give me the contour that I want, which is bad. But this will have to do then. Okay. I don't want that. How do I get rid of it? Ah. Okay. This will have to do. Okay, I'm gonna screen capture this. Okay. So we have this contour map. So far, so good. Now this is not exactly at the right level, but if we say gradient, do you remember gradient? Gradient of f. What direction does the gradient point towards? Okay, if I draw the gradient here, gradient is a vector, say, for example, on this curve at that level. Do you see gradient has to point that way, which is perpendicular, which is the fastest growing direction? Do you remember this gradient? So far, so good. So remember our f of x, here f of x, y, is equal to 2x squared plus y squared, right? And our constraint, which I'm going to put as it was this, right? And we'll call this g of x and y. So our constraint is g is equal to 1. So this is only on the boundary, not the interior. Interior, you just take a partial derivative and set it equal to 0 like we did before. This is just the boundary part. Okay, now, so gradient of f will point that way, in that direction. Good. Gradient of f at this point, then will point in this direction. Good. This is gradient of f, so I'm going to change it into good. And then let's say gradient of f down here, maybe. And let's do it right there. We're pointing straight down like this. You with me? Everywhere. Now I'm going to sketch g function. G function I'm going to say is I want that in red and I want it to fit exactly in here. So I'm going to adjust this slightly. So that fit nicely. This is my g function. I know the radius is screwed up, but suppose this is like 1, -1, and -1 to enhance our understanding. Okay? Now, I'm going to sketch the gradient of g. Where would it point to? Okay. So gradient of g, for example, somewhere here, it'll be still perpendicular to that thing right there. Wouldn't it? Perpendicular to its own curve. Are you guys getting this? Now, but at this, there's a very critical, so these two have no reason to line up. I mean, I'm going to do another one. So it's like here, it's going to point that way. But there are a few points that these two will line up, which is right here. Do you see that gradient of f and g has to line up right there? And where else would it line up? Well, this point. This is gradient of g right there. You know what I'm saying? So what we have noticed is at the local, the candidate points, which was here, one of them was 1, 0, 0, 1, negative 1, 0, and 0, negative 1. These gradient vectors line up with our contour map. You know, see this contour plot, this curve and that curve is parallel to each other. And also there, if there's another ellipse in here, then that will be parallel right there. You get what I'm saying? So here is the key observation made by Lagrange. Gradient of f is going to equal to some scalar times gradient of g at these points. Good. And then lambda is just a constant because there's no reason these two will have the same magnitude. Let's write that down. So gradient of f, remember f is this, so we have 4x and then comma 2, that's weird too, 2y will be equal to some constant, we'll call it lambda, times gradient of this, which is 2x and 2y. You with me? I know this is a kind of like big concept to swallow, but you kind of understand or agree with this? Which gives us the systems of equation. 4x is equal to 2 lambda x, right? And 2y is equal to 2 lambda y. Okay. Now, at the moment, we have, well, this thing gives us, at least we can simplify. So we have 2x is equal to lambda x, and then y is equal to lambda y. So far, so good. Now, how is it any better? Because we don't know what x is, we don't know what y is. We kind of know, but we're pretending we cannot see this picture. And then we don't know what lambda is. So this is like 3 unknowns. And we're missing one equation. So what is the third equation that we have to satisfy? And that's this one. We are only considering the boundary. You get it? So our third equation is this, x plus y squared is equal to 1. So we have converted this calculus problem into systems of nonlinear equation in algebra. Okay. You kind of with me? Kind of lost? You kind of get it, but you don't get it at the same time. It's like superposition of understanding and not understanding at the same time, like Schrödinger's cat. Okay, that's why doing a homework in this section is critical. So let's just take this first equation, okay? So I'm gonna call this equation 1, call this equation 2, and call this equation 3, okay? So I will consider 1. I'm gonna common factor, so come over to the other side. So I have x times lambda minus 1, right? That's what equation 1 is, isn't it? So from here, I get either x is equal to 0 or lambda is equal to 1. Good. So let's consider this case 1. If x is equal to 0, let's do it a little more efficiently. I'm gonna get a little more space here and go vertically. So this is case 1 and this is case 2. Good. If x is equal to 0, we really don't care about what lambda is. We want x and y coordinate. So we substitute that into equation 3. Equation 3 gives us then y squared is equal to 1. You know what I'm saying? If x is equal to 0. So y is equal to plus or minus 1. You get it? which gives us two coordinates, which is 0, 1 and 0, negative 1. Remember these two? Which is right here and right there, right? So it gives us exactly what we want to have. And case 2, I'm going to put it out there. If lambda is equal to 1, okay, now we go to equation 2. Okay, equation 2 says y is equal to, lambda is equal, did I mess up? Yeah, this lambda is not equal to 1, lambda is equal to 2, right? This equation has 2, right? So lambda is equal to 2. My bad. So equation 2 then tells you y is equal to 2y, right? What is the only conclusion in this? Y is equal to 0, right? I'm going to write it sideways. Y is equal to 0, eh? Now, if it's y is equal to 0, then according to equation 3, I have x squared is equal to 1, eh? And that tells you x is equal to plus or minus 1. So from here, I get 1, 0, and negative 1 and 0. You see, we get exactly 4 points that we wanted, that we got before from this part. You get it? Kind of get it? Now we go ahead and plug it in and do this part over. Now this may not be nicer. I mean, like, how is that any nicer than, because but I took a really nice example. In many cases, these things become pretty difficult, especially if the constraint is not nice. But Lagrange can actually convert that into algebra, systems of equation. And assuming we have enough algebra skills, then we can figure this out. You get it? Questions?
What happened to 0, 0 for the Lagrange?
Oh, this is not on the interior. This is redoing this boundary part.
Oh, so you would just do like the interior.
The interior is still done this way.
Okay, good.
Any other question? Okay, so today's topic, we have a Lagrange multiplier idea, but we have two different constrainment. Constrainment means in yesterday's session, we have a function f, but the boundary was g, right? So let's say this function is g, the yellow function. F is not shown somewhere. It's some kind of level surface in case of 3D. And then, so this was our boundary, and then gradients line up at a maximum or minimum. See, Lagrange multiplier is always about the boundary problem, not the interior. Interior, you just take a partial derivative and set it equal to 0, as always. Okay? Now, but let's say there are two different constraints, two different boundaries. Okay? And this picture could be really confusing, so let me zoom in a little bit and then try to explain what I mean. Okay, so this is one boundary and there's another boundary, which means our maximum value has to be on this curve, intersection between the two functions. You know what I'm saying? This is g and that's h function. So far with me? So what that means is our gradient is not perpendicular to g, it's not perpendicular to h gradient. It's somewhere in between. So far so good, but it's nevertheless perpendicular to that curve. It's difficult to draw it here. It's like, I can't draw it with this. But this gradient vector is perpendicular to that curve. Maybe I can draw it in here, like that. You know what I'm saying? Oh, not like that. That's misleading. It's perpendicular like that. You know what I'm saying? How can we express it? Okay. What we do is that gradient vector. See, if we draw a parallelogram between this gradient of G and gradient of H, it's gonna look like this, right? But if I extend this thing a little bit, and if I extend this a little bit, then we can actually have a parallelogram pointing at gradient of F. Do you see that picture? Do you kind of see it? Okay, I'm gonna sketch it here on a side. Say if this is I did not want to do that. This is a gradient of H according to our picture, and this is gradient of G, right? And our gradient of F is not really there, but gradient of F, let's say, is somewhere that big. Okay, let's say that's a gradient of F. Okay, what we can do is still draw a parallelogram like this. Okay, this is not as straight as I like it to be. You know what I'm saying? So if I stretch this thing, this is just dilation, right? So that length is, if I draw another vector right there, that thing is some kind of a scalar. Let's do this one. This one is a little more obvious. If I stretch this thingy, this is some kind of a lambda constant times gradient of G, isn't it? Do you see that? It's just a scaling. That's why, in fact, the reason that we call scalar is because it scales a vector. You get it? Likewise, this thing, another constant, let's call it mu, because that's what the book uses, and the gradient of H. Then this gradient of F can be written as factor addition of these two. So we can say lambda times gradient of G plus mu times gradient of H. How about that? That's what's going on here. Does that make sense to you? And this gradient of F vector is still perpendicular to now not these two surfaces, but that curve. Good. Now, and then since gradient of F, let's just write it here. Gradient, if I write this thing out, gradient of F will have partial F, partial X, partial F, partial Y, and partial F and partial Z. This is 3 variable function now. And that is same as lambda times partial G, partial X, partial G, partial Y, and then partial G, and then partial Z, plus mu, and then partial H, partial X, partial H, partial Y, and then partial H and partial Z. Once you write it like that, then we can see this F is equal to lambda of this plus mu of this. You know what I'm saying? That's F. And Y, this thing, this component of the vector is equal to lambda times this plus mu times that thingy. And so on. You get it? You look lost. If you're confused, now is a really good time. This stuff is confusing. Having said that, just looking at these, we have many, many different unknowns, right? And see, and then we create a lambda and mu. Right, we have X, Y, and Z, well, partial F, partial Y, partial Z, and then we have lambda and mu. So we have 5 different unknowns. So we need 5 different equations, and these are the 3, and then 2 constraints, right? They usually have some kind of value. So this becomes 5 by 5 non-linear systems of equation. I'm not sure that's such a better thing or not, but according to Lagrange, these type of maximum values are very difficult to achieve. So at least there's a way. Okay, let's take an example. Okay, so we have this. We have this 3-variable function, rather simple function, right? And which is on the intersection of this plane and that cylinder. So far so good. Okay. Now, can you imagine this thingy, cylinder? And then we cut it by plane, so it's some kind of space ellipse. You want me to draw it for you? Okay, let's draw it. So we have this kind of a space cylinder. Like that. This is x squared plus y squared is equal to 1. And we cut it with this thingy. Well, not that thingy, this thingy, right? And we don't know what that looks like, but we just draw it as a plane. So let's draw the plane. Like that. Then it's going to create a cross section, let's say like that. You know what I'm saying? So this is our constraint. We are only allowed to have x, y, z value that is on this space ellipse. And which one of these coordinate points give you the maximum value of this? Right, from this picture itself, looks like something that's farthest away. If this is this origin is somewhere here, and then maybe that one. You know what I'm saying? So we have to find that point. You with me? Okay, so the way you set this up is first we take gradient of f. So gradient of f is we differentiate this with respect to x, so you get 1, the other 2 dies with respect to y, so the other 2 dies, and with respect to z. See, without doing it with the Lagrange multiplier, now it's not even imaginable. How are we going to maximize that value on that space ellipse? One way is to figure out the parametric equation of that space ellipse and then plug it in. I mean, that's one way, but that itself looks pretty complicated. And then other problems gets a lot more complex than this, okay? So, and then we find the gradient of g. And our g, which one should we say is g and which one is h? Let's say this is g. This is g right there. And this one is h, okay? So gradient of g, so we have 1, -1, and 1. Good. And then we find gradient of h. Now that h looks weird. And then that will be 2x, 2y, and 0. So far so good? Are you with me? Then we plug it into this equation. Gradient of f is equal to mu times gradient of, well, that's not gradient. gradient of G plus mu. Let's go with the book. Lambda first, then mu of gradient of H. Okay? So what that gives us is this thingy, 1 is equal to lambda plus 2 mu x. Do you see that? And 2 is equal to negative lambda plus 2 mu y. And finally, 3 is equal to, once again, lambda, and then times mu times 0. So this is it. Good. Wow, we got lucky because at least we know what lambda is, right? So these two equations simplify quite a bit. Lambda is equal to 3. Okay, so that tells you 2 mu x divides, so mu x is equal to negative 1. And here mu y, because lambda is equal to 3, right? So 5 over 2. So far, so good. Now, there's no orthodox way of solving this because these are nonlinear systems of equation, but let's take this thingy over that thingy. We vertically divide, that way at least we can eliminate mu. So y over x is equal to negative 5 over 2. So far, so good? Say yes. Now what do we do? Looks like we need another equation. Suggestion. Well, we have option for this or this, right? But I do not want to use this one because that still it introduces z, which is another headache. So I'm going to go with h, use this constraint h. Okay? So x squared plus y squared is equal to 1. So we are going to substitute this into x squared plus y squared is equal to 1. Okay? Well, I'm not going to substitute that expression because that looks weird. So let's say y is equal to negative 5 over 2x and then substitute that in. How about that? Good. So we'll have x squared plus 25 over 4, x squared is equal to 1. Eh? Say yes. Okay, so if I add, that's 29 over 4, right? So x squared is equal to 4 over 29. Eh? So x is equal to plus or minus 2 over square root 29. Good. Say yes. Now we plug it in to this thingy right here. So multiplying negative 5 over 2, so 2 cancels, so we'll have minus plus, and then 5 over square root 29. Still with me? Say yes. And then we plug both of them into z, which, well, we can plug it into this thingy, right? And this is too much algebra, so if I cheat, I mean do it in my head, this will be 1 minus plus 7 over square root 29. How about that? So this is in a way that converting calculus into algebra. And now we have to find the max, right? So therefore, my max, absolute max, is f of negative 2 over, and 1 is positive. It's like you have to plug in the right one, and then maximum turns out to be this combo. And then 5 over square root 29 and 1 plus 7 over square root 29, and that will be 3 plus square root 29. And the other combo will, I think, will give you a minimum. How's that?